Okay, geometry fans, our topic for today, section 8-3, special right triangles. You'll be taking these notes on your own paper. Before we start, let me give you your joke of the day. A burglar stole all the lamps in my house. I know I should be more upset, but I'm absolutely delighted. Delighted? No lights. Okay. As mathematicians, we are constantly looking for patterns. And what happens is that when you have certain types of right triangles, there are patterns that show up, that exist, that allow us to find answers, to find values faster than using the Pythagorean theorem. There are two types of special right triangles that we're going to look at. The first one is called a 45-45-90 right triangle. The 45-45-90 refer to the angle measures. Now, there's the 90-degree angle for a right triangle, but then we're saying that both of these other angles are the same, they're 45. Now, one thing that you might make a connection to is that, well, when the angles are congruent, so are the opposite sides in any triangle. So what happens is these two sides are the same. Now, 90 is always opposite the longest side, the hypotenuse. So the hypotenuse is not the same as these. But you could call this an isosceles right triangle. It is an isosceles right triangle. So these sides are congruent. Now those are the legs. The legs are equal, their lengths. And then the hypotenuse is, of course, the longest side. Okay, now something's going to happen to the values, the measures of the sides in an isosceles right triangle. As an example, let's say that the two legs were 4 and x is the hypotenuse. Well, we can solve that. We can do Pythagorean theorem. A squared plus b squared is equal to c squared. And this would be 16 plus 16, which is 32. Now, to solve that, to undo a square, we need to take the square root of both sides. This is x. That's not a perfect square, but we can simplify that. That's 16 times 2. And the square root of 16 is 4, so we pull that out. And the answer is 4 square root 2 is equal to x. Now, something to notice here is that 4, those are the legs, and the hypotenuse is 4 square root 2. Interesting, they're all 4s. Well, let's take another example. Let's say that we knew, again, 45-45-90. Now this time I'll just draw these congruent. I won't put the 45s there. Let's say that these are 3. The legs are 3. So 3 squared plus 3 squared is x squared. That's 9 plus 9, which is 18. When we take the square root of 18, you can say that is 9 times 2. 9 is perfect. Well, the square root of 9 is 3, so we get 3 square root 2 is equal to x. 3, those are the legs. The hypotenuse is 3 times the square root of 2. Now, you may be wondering, wait a minute, is that going to happen for every 45-45-90 triangle? And the answer, I'll put the 45s in here, the answer is yes. That is always going to be true. That whatever the legs are, if they're 4 and 4, then the hypotenuse is 4 times square root 2. If it's 3 and 3, the hypotenuse is 3 times square root 2. If it was 11 and 11, the hypotenuse would be 11 times the square root of 2. So what happens is, I'm going to redraw this over here. There's a ratio that comes up. Okay, and the ratio, what I'm going to do is compare the legs. I'll write it down here first. Okay, 4 to 4. And then the hypotenuse is 4 square root 2. Now remember, a ratio is a comparison of numbers using division, basically. I could simplify this by dividing each of these by 4. And what we would get is 1 to 1 to 1 square root 2. Which I'm just going to write as the square root of 2. If the measures of the right triangle are 3, 3, 3 square root 2, this time we could divide by 3 to reduce, and we would get 1 to 1 to the square root of 2. So the way that I remember this is that when we have a 45, 45, 90 right triangle, the ratio of the sides is always 1 to 1 to the square root of 2. 45, 45, 90. Those are the angle measures. And the ones are the ratio of the legs. So leg, leg, hypotenuse. This is how I remember it. Okay, you can see, if you look in a textbook, what they'll typically show you is this, 1, 1, 1 square root 2. That's what it looks like in the picture. But I find it easier just to work in the ratio, and I'll show you how. Now, with this, I'm going to give you a bunch of examples. So, example. Now, this is only for a 45, 45, 90, which is isosceles. So, let's say this is 7. Here's x, here's y. And we want to find the missing sides. Well, in a 45, 45, 90, the legs are in a 1-to-1 ratio, so they're equal. If this is 7, the other leg is 7. So right away we know that. Now, to go from a leg to a hypotenuse, what we do is we multiply by the square root of 2. So I'm going to write that as times the square root of 2. When we move forward in the ratio, we're going to multiply. So 7, 7, 7 times square root 2. Now we don't put the times symbol there, we just write the numbers next to each other. That's it. You could do Pythagorean theorem, but why would you do that if you have this nice pattern, if you recognize the pattern? Okay, example. Let's say, I'll draw it a little bit differently. Let's say the legs are 103. Here's x, here's y. So again, we want to find the missing sides. Well, the legs are congruent. There's 103. How do I go from a leg to a hypotenuse? In a 45, 45, 90, we multiply by the square root of 2. So we take 103 times square root 2. That's it. You're done. So you can do this without really doing any kind of work. All right, what if, let me change it up here. Let's say we have a right triangle, 45, 45, 90. Let's say that the hypotenuse is 8 square root 2. So this time I'm going to give you the hypotenuse. Here's x and here's y. Now we have to identify it's 45, 45, 90, and it is right there. So how do we go from the hypotenuse back to the legs? Well, in the ratio 1 to 1 to the square root of 2, when we move forward, we multiply. When we move backwards, we divide. So to go from the hypotenuse back to a leg, we divide by the square root of 2. Okay, now again, you can do this without work, but you're going to take 8 square root 2 and divide by the square root of 2. Well, any number divided by itself is just 1. So that reduces to 1, and what you're left with is 8 and 8. So in other words, whatever this number is in front of square root 2, that has to be the value of the legs. All right, example. Let's say we have a square. And let's say that, here I'll write down square. Let's say that I draw a diagonal, and the diagonal is 9 square root 2. And what we want to find is the legs. Okay, here's x, the sides of the square. Okay, I'll just use x. Well, what we have to understand here is that when we draw the diagonal, we have created an isosceles right triangle, which is 45, 45, 90 for the degrees. If the hypotenuse is 9 square root 2, how do we go back to a leg? We divide. So 9 root 2 divided by root 2, we get 9 and 9. So the lengths are 9. If I asked you for the perimeter now, if I extend it, the perimeter would be 9, 9, 9, 9, or you could just say 4 times 9, which is 36. Okay, so there are different ways that I can ask you this question. That's it. You can look at these and immediately you can write down the answers. Now, you might be asking, that's it? That's pretty easy. Does it get harder? Well, there's one situation you have to be aware of. Let's say that the hypotenuse was 10. Okay, again, it's a 45, 45, 90. To go from the hypotenuse back to a leg, I have to divide by the square root of 2. What happens if I don't have a square root of 2 to start with, though? Well, we're going to take whatever the hypotenuse is, we're going to divide by square root 2. Now, that is not simplified. What we have to do is called rationalizing the denominator. What I'm going to do here is multiply the top and the bottom of the fraction by the square root of 2. When you do this, the square root of 2 times the square root of 2 is the square root of 4, which is just 2. So what happens is that in the denominator, the square roots undo each other, and all you're left with is the number 2. And then up top here, 10 times square root 2, well, I can't combine those, I just write them next to each other. And the last thing to ask is, can you reduce the outside numbers, 10 and 2? Yes, that would be 5. Okay, so our answer is 5 square root 2. So the measures of the legs are both 5 square root 2. So that's the only time that you really need to do work. Okay, example. Let's say it's an odd number. Let's say it's 13. And here's x and here's y. How do we go from the hypotenuse back to a leg? We divide by the square root of 2. Now that's not simplified. You cannot have a radical left in the denominator of a fraction. So what we do is we multiply by the square root of 2 over itself. I call this a fancy form of 1. Fancy form of the number 1. Because a square root of 2 divided by itself, anything divided by itself, that's really just 1. So when I rewrite this and I say 13 square root 2 divided by, this just becomes 2. This is equal to this fraction here. All I've done is change the way it looks, but I haven't changed the value. Now, since 13 and 2 cannot be reduced, this is a good answer right here. That's going to be your x and that's going to be your y. Now, you might ask, could I write it as 6.5 square root 2? You could, but we don't usually write a decimal with a square root, with a radical. If you wanted to, you could write it as the fraction 13 halves and then times square root 2 like that. But this is just as good, and we would just keep it like that. So that's the only situation where you would even need to show work, is that if you're going from the hypotenuse back to the leg and you divide by square root 2, but there's not already a square root of 2 attached to it. And that is the end of part 1.